Hi there, I'm here to talk about Completely Fair Scheduler. Sit back and listen. What is Completely Fair Scheduler? It is based on Rotating Staircase Deadline Scheduler or RSDL. It is the default scheduling process since version 2.6.23. Elegant handling of I/O and CPU-bound process. Idea behind CFS. Each run-able process has virtual time associated with it in PCB, process control block. Whenever a context switch happens or at every scheduling point, then current running process virtual time is increased by virtual runtime per process plus equals t, where t is time for which it is executed recently. Runtime for the process therefore monotonically increases. So this way each process gets fair time for the execution as after every context switch the virtual time of a process increases and thus priority shuffles. Completely fair scheduler. According to Ingo Molnar, the author of the CFS, its core design can be summed up in single sentence. CFS basically models an ideal, precise multitasking CPU on real hardware. Let's try to understand what ideal, precise multitasking CPU means. As the CFS tries to emulate this CPU, an ideal, precise multitasking CPU is a hardware CPU that can run multiple processes at the same time, in parallel, giving each process an equal share of processor power, not time but power. If a single process is running, it would receive 100% of the processor's power. With two processes, each would have exactly 50% of the physical power in parallel. Similarly, with four processes running, each would get precisely 25% of physical CPU power in parallels and so on. Therefore, this CPU would be fair to all the tasks running in the system. The CFS tries to eliminate the unfairness from the system. The CFS tries to keep the track of the fair share of the CPU that would have been available to each process in the system. So CFS runs a fair clock at a fraction of real CPU clock speed. The fair clock's rate of increase is calculated by dividing the wall time in nanoseconds by the total number of processes waiting. The resulting value is the amount of CPU time to which each process is entitled. As a process waits for the CPU, the scheduler tracks the amount of time it would have used on the ideal processor. This wait time, represented by the per task wait runtime variable, is used to rank processes for scheduling and to determine the amount of time the process is allowed to execute before being preempted. The process with the longest wait time that is with the gravest need of CPU is picked by the scheduler and assigned to the CPU. When this process is running, its wait time decreases, while the time of other waiting tasks increases as they were waiting. This essentially means that after some time, there will be another task with the largest wait time in gravest need of the CPU, and the currently running task will be preempted. Using this principle, CFS tries to be fair with to all tasks and always tries to have a system with zero wait time for each process. Each process has an equal share of the CPU, something an ideal precise multitasking CPU would have done. In order for the CFS to emulate an ideal precise multitasking CPU by giving each runnable process an equal slice of execution time, CFS needs to have the following: a mechanism to calculate what the fair CPU share is per process. This is achieved by using a system-wide run queue fair clock variable CFS RQ fair clock. This fair clock runs at a fraction of real time, so that it runs at the ideal pace for a single task when there are n runnable tasks in the system. For example, if you have 4 runnable tasks, fair clock increases at one-fourth of the speed of fall time, which means 25% fair CPU power. A mechanism to keep track of the time for which each process was waiting while the CPU was assigned to, to the currently running task. This wait time is accumulated in the per process variable wait runtime, process to wait runtime. But rather than maintain the task in a run queue, as has been done in prior Linux schedulers, the CFS maintains a time-ordered red block tree. A red block tree is a tree with a couple of interesting and useful properties. First, it's self-balancing, which means that no path in the tree will ever be more than twice as long as any other. Second is operations on the tree occur in O log n time, where n is the number of nodes in the tree. This means that you can insert or delete a task quickly and efficiently. With tasks represented by sched entity objects stored in the time-ordered red block tree, tasks with the greatest need for the processor, lowest virtual time, runtime, are stored toward the left side of the tree, and tasks with the least need of the processor, highest virtual runtimes, are stored toward the right side of the run tree. The scheduler then, to be fair, picks the leftmost node of the red block tree to schedule next to maintain fairness. The task accounts for its time with the CPU by adding its execution time to the virtual runtime is is then inserted back into the tree if runnable. In this way, tasks on the left side of the tree are given time to execute and the contents of the tree migrate from the right to the left to maintain fairness. Therefore, each runnable task chases the other to maintain a balance of execution across the set of runnable tasks. Time complexity analysis of the CFS. Insertion in red block trees takes O log n. Finding the node with lowest virtual time is O1 as we can maintain a pointer. In maps, we can use auto IT is equal to map that begin. So overall time complexity is O log n. Here, red block tree is once created and then we have a red block tree of n process. So the scheduling time complexity is O log n. There is also one advantage of using red block trees that is if a process is IO bound, then virtual time is going to be very less and it appears as the leftmost node in the red block tree, so executed first. So CFS easily figured out the process which are IO bound and which are CPU bound, and it gives higher priority to IO bound process, so avoiding the starvation. So that's all. Thank you for watching.